Hello, my name is Juan Arreola. I am a physics student at UCR, and I'm currently at Cornell doing an RU for class summer 2024. And my project is on high quality factor normal conducting cavities, and seeing what material is best for such operation. Hopefully it's not just copper. Yeah. We start by imagining a cavity, and we want to keep this cavity cool. So to keep it cool, you want to minimize the surface resistance. Now, you probably have heard of electrical conductivity, but chances are you probably haven't heard about the skin depth. It's okay, neither did I 10 weeks ago, but essentially what it is how far the RF field penetrates the cavity surface when it is incident upon the bulk of the cavity. To speak of low power dissipation is to speak of high quality factor, so TLDR, the higher the better. For our analysis, we have to talk about the mean free path. Now, the mean free path is how far the electron can travel without getting hit by some impurity or structure or another electron. Typically, as temperature approaches zero, this becomes very long in a good conductor. And as that happens in a conductor, the skin depth begins to decrease and become very small. At a certain point, your mean free path becomes comparable or larger than the skin depth. And when this happens, weird stuff happens. Some might even call it anomalous. Investigation of this anomalous behavior is essential to my project. Here's a graph of your typical ohmic behavior, or what you would expect to see the surface resistance do at low temperatures. But unfortunately, this is not the case and looks more like this, plateauing much quicker than expected. This is known as the anomalous skin effect. With this relationship no longer valid, we must modify our model to account for this anomalous behavior with derivations by Hassam Badamsi. We cannot rightly talk about conductivity without first talking about resistivity, and Mathiassen's rule does this with flying colors. Mathiassen's rule is characterized by sum of the intrinsic and the residual resistivity, with the residual characterized by purity of metal and intrinsic being characterized by phonon interactions. Phonons are quantized vibrational energy as photons are quantized electromagnetic energy. The residual resistivity can be straightforward to find, but the intrinsic requires more sophistication with the Bloch-Grunheisen formula modeling it to a sufficient accuracy. With that, we have our key tools for our analysis. The metals of interest are gold, copper, aluminum, and silver. Cavity performance and comparison will be done in a temperature range that is typical of a liquid nitrogen regime. This is done so as to simulate the conditions proposed by the cool copper collider over at SLAC, which at the time is currently the most substantial effort towards a normal conducting direction. At 77 degrees Kelvin, copper was found to be the best material for cavities, closely followed by aluminum. This result wasn't entirely surprising, but what was interesting was that aluminum took over copper at around 70 degrees Kelvin. Furthermore, new research at SLAC has shown that copper-silver alloy may be a better alternative to pure copper. With that being said, I'd like to say thank you to my mentor, Matthias Lippe, and to CLASSE for giving me the opportunity to conduct research this summer in accelerated physics. Special thank you goes to the National Science Foundation for funding my research.